Lost in cold, twisted minds in overload, unfornicated decoys, shattering the fragile abode. Whispers in the endless void, chasing ghosts they can't avoid. Chamber sounds abound. Unfornicated won't be bound, tearing myths from the ground.
Well, hello, everybody. Welcome back. Look who's back. It's me. Welcome back to Unfornicated, your speakeasy of the truth. I am your all-knowing bartender who doesn't know shit. Make sure you have your drinks ready tonight because we have a bit of a surprise. So part of the rebranding for the channel, what we're doing is adding a few things. Excuse me. And one of the things that I want to do is a new series that kind of brings citizen science back into the mainstream. Stuff we can do at home to kind of prove the world around us. And in essence, I don't know. I guess the best way to do is let's drive interest back as science. Now, as a parent, it's something that's a little more, I guess you could say, prominent in what I try to do. I figured this channel is going to be part of that. So besides the point in laughing, besides the mocking, besides all the other stuff that this channel is known for, we're going to take it up another step, and we're going to start doing these new segments that I call field notes. So field notes are simple. It's basically the same thing that you would know about this channel. It's about receipts. It's about actually doing it. It's about asking experts for help and basically learning, because that's what we'd like to do. And that's what field notes is going to be. No grifters, no cranks, none of that silliness. It's all going to be easy, simplistic things that we can do without a minimal or with a minimal of investment. No high-priced equipment. No accuracy to the 10 to the negative 17th decimal points. You know, it's ridiculous. But real results. So for tonight's very first stream, it's a little, it's going to be a little bit more than maybe that, but I think it's a good gateway for us to get into this. So, simple question. How fast is the Earth moving? Seems simple. You know, we're taught certain things in schools, and we're able to verify certain things through authorities. But now we don't have to. So not theoretically, not from a textbook. This is going to be actual measurements from the ground with a radio telescope, with a radio dish. So my guest tonight, I have multiple guests, but the guest of honor tonight, I guess you could say, took Doppler measurements of the 21 centimeter hydrogen line. It's basically the fingerprint of neutral hydrogen distributed across interstellar space. And extracted from that data, Earth's orbital velocity, the distance to the sun, and the mass of the star we orbit. Then he pointed his dish at a pulsar, or rather, one of his coworkers, pointed the same dish or a different dish at a pulsar, which is basically a neutron star rotating with the precision of the finest clock in the known universe. And what they were able to pull from that was not only Earth's orbit eccentricity, but it was also accurate to 0.036%. Oh, and they also found the moon hiding in the residuals, but we'll come back to that. But don't worry, Newton would approve. So tonight we have Marcus Leach. He is the president and observatory director of the Canadian Centre for Experimental Radio Astronomy. It's a long-ass title. We also are joined by other content creators. Let me bring them up here on the screen so you guys can all say hi. We have also with us Astro Kate. We also have Gabe from Save It From Parts. And we also have Astronomy Live. So this right here is the largest collection of radio nerds I could find. And with that being said, hold on, let me find my cursor all of a sudden, so that way they can hear me too. I didn't realize I muted myself from them as well. So this large collection of radio nerds I have here, myself included, is the absolute perfect people to put Marcus's experiment or observation through the ringer. This collection of people is basically going to be people who will find the flaws. They will find the inaccurate measurements or like the nuances, because background matters, experience matters. And again, this is what we want. We want to test science. So this is what we're going to do. Now, we all talk about science and how there's certain people in this world who can't science. Well, this is going to show them what real science really looks like. So here we go. All right. Let's see. Hold on. Do I still have echo? Oh, you know what? I do. Hold on a second.
I don't hear any.
No, I think Gabe's mic was up. If you were pulling in that audio, it would have produced an echo, but it was gone at some point.
Well, sorry about that if it was
Thanks,
mine.
Gabe.
No
Way
problem.
to knock my screen, my live stream down to professional level or 3. I do that on my own. I don't need help. All right, so here we go. Now, here's what we're going to say. A little extra thing that we're going to work on here is Marcus is also going to take us on a tour of the observatory. So you guys get to see a class act presenting an actual real tool. And the other part of this that we're going to also discuss is how, if you are so inclined, you can do this experiment from home. So with that, Marcus, I will turn this over to you.
Okay, thanks, Dan. Do we want to introduce all the other people here? Or did we already do that?
Did that? I mean, you guys, I think everyone knows you guys who's here. But if, we can actually do a couple things real quick. Here's what we're going to do. We're going to start in upper left-hand. Actually, no, we're going to start in the upper right-hand corner because ladies first. Astro Kate, would you be so kind as to provide just a quick introduction of who you are, what your specialty is, and why you're on this panel?
Sure. I am a radio ham operator, extra class, as well as an RF engineer as part of my job. I specifically work very closely with RF signals from space, particularly from spacecraft for a living. So I'm very well familiar with receiving and sending radio signals to and from space.
Great. Gabe, let's start with you next.
Sure, and hopefully I'm not echoing again because I can't get a headphone to work on this laptop. But yeah, so my name's Gabe. I run the Save It For Parts YouTube channel, and I do a lot of things, but the satellite content got really popular, so I do a lot of amateur satellite experiments, a little bit of radio astronomy, although I'm not as good at that as I am with some of the satellite stuff. And a lot of my projects are kind of on a dumpster diving budget, so I do kind of citizen science with stuff I can find in the trash or build or scrounge together as much as possible.
Perfect. And of all the channels that we have here, Gabe is the one we kind of aspire to because he now has topped 369,000 subs. Gabe, is that right? Something like that.
Something
Yeah,
like
he
that,
lost
yeah.
count a while ago. Congratulations on hitting that number, and congratulations on some of your projects. It's been great watching some of the stuff on your channel. I greatly appreciate what you do, since that's kind of what I do too. Is just kind of like what everybody on this panel does. Is everyone's a little bit of a MacGyver and kind of just does shit to make it work. So, okay, seems okay again. It's Jesus Christ. All right, we'll figure out the echo. Just give me a minute.
It might be me.
No,
can
I
play
turned down
around
my
with the,
gain because it's specifically when you talk for some reason. I think it's the tone is close to mine, so it's picking it up off my monitors. But I'll figure that out.
I'm gonna say I might be the only one without headphones.
No,
but,
I'm without them too, so
yeah, I'm
don't
not
forget
sure.
that.
So. Okay.
Astronomy Live. How about your turn?
Oh, all right. So, of everyone here on the panel, I'm probably the one with the least amount of radio experience, but I do a lot of astronomy, a lot of optical tracking, both of satellites and just astronomy in general. So I've done measurements of Earth's orbital velocity using aberration optically, looking at velocity aberration. So attacking the same question, but from a different perspective, from a different methodology. So earlier, well, actually now last year, in 2025, I conducted measurements over several months of Barnard's star. For one thing, to measure the parallax and the distance of Barnard's star, but also within those images, over months of time, the field of view changes. So if you find two nights with the same temperature, so that the telescope is experiencing the exact same conditions in terms of thermal expansion of the tube, and you compare those images months apart, you'll see the field of view is still different because of the fact that at one point you're looking along Earth's direction of travel, and the other point months earlier you're looking in a different direction. So by comparing those images months apart, I was able to detect velocity aberration in the images. But now I'm curious to see what Marcus has to present, and I'm really interested in getting into some more of this radio astronomy stuff I've been hearing so much about. So now I've got a dish out back that I'm starting to outfit. I already started receiving images from the GO satellite thanks to Gabe's channel and some information I learned there on Save It for Parts. But now looking at what Marcus is doing to see if I can replicate some of his methodology as well.
All right, sounds perfect. And last but not least, our guest of honor, Marcus, would you like to do a quick introduction with yourself? And I will turn the stream over to you.
Sure. So I'm actually currently sitting in the what we now call the event space at this observatory building, formerly a NATO facility. And we moved in here 4.5 years ago, I guess, to take over operation of the big dish here, which was basically just a lawn ornament for the 25 years that the building owner owned the place. And we were the first people to come along and say, hey, we can probably use it for some stuff. So that's where we are now. This room would have been the op center for it was basically, this was a NATO SATCOM terminal. So there would have been, a few dozen people in here with equipment and all of that stuff, essentially connecting phone calls from the equivalent of the DTN to, satellite channels. That's what they did here. And it tracked a couple of different satellites during its time. But yeah, I'm the observatory director and the president of the organization that runs this little part of the building. The building's used for multiple purposes.
Perfect. So as you can see, I'm the outlier here who probably doesn't belong on the panel, but I digress. Hey, it's going to be great having this collection of people here. Hopefully, Marcus is going to go through his presentation, explain a lot of different things, as well as provide us a tour. And then at the same time, we get to put him through the ringer and start asking some questions. And one of the best parts about this is that Marcus is going to explain how we can do this too. So we'll go from there. Well, kind of like what Astronomy Live was talking about. Astronomy Live is actually, we've been trying to schedule this for, I don't know, months. And part of the problem we've had is, work, illnesses, we all have jobs and things like that. And In the meantime, Astronomy Live has been putting his solar cooker up in the yard and has been actually talking to this group chat about different things that he needs to get done to help facilitate some of these things too. So one of the best things I love about being a content creator, especially in this community, is the people I get to meet. And this collection of people right now are the people who that are part of that group that I'm happy to have met and at least, virtually, and can rely on their expertise to do things. So let's, what do you want to do next?
So what I'm going to do, my plan is to do the tour first, and when I come back downstairs from the tour, we'll launch into the presentation. So I will probably drop away and then come back because I'll be switching to my phone.
Let me just switch. I think
just
it
make
brings
that
you
happen
right back without having to do the whole drop thing and everything else.
Yeah, well, we're about to try it. So I go to this.
We still see you. I see you on your phone. There we go. All right, I'm going to go ahead and make you large.
Using a fat camera. Oh, hang on.
Show us your passwords, please.
Oh, wait, hold on.
Okay, I have to switch headphones.
Okay. Yep.
Can you hear me? Okay. All right. So I'm going to put the camera in the.
Yep.
I think that's correct.
Landscape. Thank you. Yes.
In the holder, and you guys should basically have a point of view of what I'm doing.
Yep.
Are you there? Yeah. Okay. Sorry. I might need to ask if you're there. There's like no comfort noise on these headphones, so we're going to head upstairs to the dish. There's a stairway that's quite steep.
If someone has the Canadian number for 911, just in case Marcus decides to take a spill, let us know.
Well, I haven't done it yet, but you never know. So we're coming up to this hatch here that you can probably see. And now we're up into the radome.
It's very
echoey up here. Do I still have a
You're
connection?
not coming across as an echo, so whatever headset you have, it's doing a good job.
Oh, great. So you can see the radome here. It's about 20 meters in diameter, 22 meters in diameter. Put in 1971, and the material here is from 1971. It's basically a fiberglass composite with steel structure to support it. There's the dish. What I'm going to do is come around the front of the dish, at least part of it. If I go to the very front, I might lose the signal.
Yep.
Can you guys see it?
Yes.
Perfect. And what I will do is I'll tilt this up. So you should be able to see the feed assembly.
And that's a 13-meter dish, right?
If I go all the way in, it's 12.8 meters. Yeah. Yeah. So 42 feet for, Douglas Adams fans. Yeah. If I go all the way in front, it'll probably block the signal from the Wi-Fi router, which is just over there.
Oh, we get to go in the restricted area. Look out.
Yeah. Yeah, I'm authorized personnel, as it turns out. This here that you can see that says caution, disconnect motor power before entering is the cable management chamber, also known as the clock spring chamber. And the cables are actually wound through something that looks like a, early 20th century clock spring. So what happens, the cables that are going through the azimuth axis, they get wound up and unwound rather than twisted when we're moving the azimuth axis. Yeah, I mean, anything that moves like this, the cable management is even more of a problem. So over the years, various, satellite or radio telescope people have figured out different ways to do it. I've been to lots of different radio observatories, and each of them does it differently. So this is our azimuth cabin. You're all still with me?
Yes.
Okay, so I'm going to have to keep asking because the signal here is not that good, even with the Wi-Fi access point at the bottom. So as I go into the azimuth cabin, the signal should be okay, but I don't know. But so we're going to go in. This is our lovely little control facility here. And that is the elevation cabin. Can you guys see it?
Yeah.
Okay, cool. So the elevation cabin moves with the elevation axis. There's a platform in there that you can stand on, and when the elevation axis is moving, the entire room moves around you. So we've got an equipment case there. If I go into the elevation chamber, I'll almost certainly lose you because you can see it's all steel. So we've got a 4-channel software-defined radio receiver. There's a turquoise cable, which Dan won't be able to see as turquoise, and I apologize. And it is basically an 8-strand 10 gigabit cable. And that's how we connect to the computers downstairs. So if we go back out again, we have the what's called the motor chamber or motor cabin. I'm not going to go down there because, again, I'll probably lose the signal. But all the motors and the main parts of the motion control system are down there, and the big heavy gearboxes.
So in other words, you're saying this is a significant amount of engineering.
Oh, yeah. Yeah, the gearboxes weigh 750 kilograms a piece, and there's 4 of them down there. And they used to be 8 7.5 horsepower DC motors, 7.5 horsepower DC motors. They were big. They weigh 85 kilograms a piece. And we had to devise a mechanism for getting them out and lowering them down to the bottom, which is what that crane is all about. And of course, that's down to the bottom. So what we're going to do is, can you see the power control box from here?
Yeah.
Cool. I'm going to bring up the power. I'm going to use the right key to bring up the power.
Oh, look at that. You have 2 different buttons, elevation and azimuth. Wow. Go figure.
So I'm going to bring up the power. I'll press the start button. And
Also,
okay, so the power is...
Thank you for showing us your keys on screen. I appreciate that.
Oh, geez. Yeah. So, I mean, so Caitlin's going to cut a key and sneak up here one night and power up the dish.
Do not put it by her.
I don't know if any of you have noticed the blue button here. Can you see the blue button? Yes, phasers, random spread. Yes, that blue button does nothing, but the box that I used was it was used and it already had a hole there, so I put a blue button in it. What I do is I tend to change that sticker every few months. So when we have people coming through here on tours, they get a different experience every time. The first one we had was when I was dealing with a lot of grad students who were dumb as a bag of hammers. And so the button was labeled, "Write my thesis."
Everyone wants you to hit the big reset button.
Yeah,
that's because they're all chaos agents. They just want to hit the big red button. They have no self-control.
So I brought up the motion control server, which means both brakes, the elevation and azimuth brakes, are now off. So I can command a motion. So what I'm going to do is I am going to command the dish to move up a few degrees and over a few degrees, just so you can see it. So about 20 degrees, or 220, and I don't know, let's call it 40.26.
We're not screwing up any experiments, right?
Not really. We have a long-term observation we're doing, but it won't matter if we interrupt it for a few minutes. So you can see now that the dish is moving, and you might be able to hear it in the audio as well.
Oh, yeah, we can see it moving.
Oh, yeah.
Yep. So it's coming up a little bit and moving to the west a little bit.
There's a lot of weight to move.
It's actually surprisingly light. It's only 5.6 tons. But, that's much more than an amateur dish, that's for sure.
What's the slew rate? What's the maximum slew speed?
Well, it's doing that right now. The maximum slew speed in azimuth is 22.5 degrees a minute, and the maximum slew speed in elevation is 9 degrees a minute. So it can barely keep up with low Earth orbit satellites. It was basically budgetary constraints and the size of motors we could afford and the amount of power we could bring up. And our main thing here is astronomy. So,
yeah, that makes sense.
So if we look at the, come back in here, we can see the elevation and azimuth readouts.
Oh, yeah.
Yep. You guys can see that. Yeah.
That is really cool. See, these are the kind of play toys I want.
Yeah, dishcontrol.py. I like that.
Sorry, what?
Dishcontrol.py, your Python script?
Oh,
Yeah.
oh, yeah.
I was going to say, that looked like Tikenter to me on the interface.
Actually, the manual motion application is actually written in GNU Radio because it was really fast and easy to do. So it's not actually processing any radio stuff in it. It's just that the UI and the data flow architecture means that it took me literally like 20 minutes to get this particular application together. Okay, so it's now done with that, and I'm going to move it back to where it was.
Yep. In the meantime here, I have some suggestions of what you should label the blue button next. From Joe Black, sure. He says, label it "Don't Destroy Earth."
Oh, yeah, sure. Yeah. Yeah. Do not push this button, that kind of thing.
I think that works better with the big red one, though.
Yeah, well, the big red button is the emergency stop.
It's a pain to reset afterwards, I'm sure.
Yeah, though basically it's an old school emergency stop button. It was the one that was here originally, and we moved it up here and decided to keep it. But the old school emergency stop buttons, the way you reset them is there's a button on top of them that you have to push to reset the e-stop. Modern e-stop controls, you push them, and then they kind of do this bayonet lock thing, and you have to twist them to get them to pop out again.
I have a suggestion for the blue button label. Should label it "Penetrate the Firmament."
Oh, yeah, yes. I can do that sometime.
Let's flood Earth. Real Harlem had a valid point here. He said he's seen Howard the Duck, and I have too, many times. And he knows how this ends.
Oh, I don't remember Howard the Duck that much.
It is by far rated the absolute worst movie ever made. That's what makes it funny.
I think I've only seen it once when it first came out. And, I remember the theme song. That's about it. So you guys can't hear this, but as the mechanism gets closer to the target, it slows down, and it does it on an exponential schedule so that it stands almost no chance of ever overrunning its target due to, inertia.
Right, no sudden stops that are causing stress on the brakes and things like that.
Yeah, well, we actually did an experimental. The first time we did tracking, we did what's called, it's basically a stop and wait approach where you kind of wait for the sky to catch up with you and then move, and then wait for the sky to catch up with you and then move. And it was horrible. The structure hated it. Like, it was like, do not do this to me again. So I went back and wrote some more code, and now our tracking code is a continuous tracking, and it's really, really easy on the structure.
Do you ever have to calibrate? Oh, do you ever have to calibrate the pointing location ever, or is it just sort of fixed from the beginning?
We do have a mechanism for doing that, but we haven't had to use it so far. The pointing mechanism is actually quite reliable and repeatable. It's, and they were only $200 a piece, so that's pretty cool. Okay, so I've shut down the motion control server, and I'm stopping the power, so it can't be moved now. Even if Caitlin hacks in from,
from 3,000 miles away,
it's not going to happen. Yeah. Okay, I'm heading back down again, and what I'll show you is one of the mechanisms we used for doing alignment. So right here, that I don't know if you can see it. There's like a little silver bar right there.
Yeah.
Do you guys see it? Okay. There's a laser in there. There's one of those leveling laser thingies. And then on the wall, I don't know if you can see that.
Oh, yeah.
There's a target. And so what we do is when the dish is pointing exactly south, the laser will be in the middle of the target, and the rings on the target are 1/10 of a degree.
Oh, wow. Okay.
Yeah. Okay, so we're going to head back
All right,
downstairs.
we got some other suggestions for the
If anybody wants
blue
to go-
button. Don't touch, obviously, is a big one. Canadian Space Advocate says it should be labeled Zoom. Copium Emporium said enlarge moon, or, call it the moon tractor beam, so that way we can start the whole don't look up thing.
Destroy a space station?
Well, it is a Mars
like from
Uber,
Star Wars?
so, it's probably magnetic.
Right. I'm just going to lock up the hatch here.
Max has got the best one. Self-destruct.
What about ludicrous speed?
Yep.
Oh, yes. Yes. That's from Spaceballs, right?
Yep.
I am seeing a couple questions here real quick for you, Marcus. So when you get settled back to your laptop.
How about I get back on my laptop, and then we'll do those.
All right. Marcus is going to log back in here. So if you guys have questions regarding the telescope, by all means, go ahead and tag me in the chat, and I'll read them out for Marcus, and we'll get some answers for you, and then we'll move on to the presentation. And since we had a little bit of a stream issue at the time, we're going to make this work a little janky way to make it work. I'm going to be moving the slides while Marcus narrates. Initiate mind control beam. No, that's at heart, Blackburn. All right, there we are.
Okay. I had to grab some water because my voice was starting to crack up top. So
you need rum instead. It makes it better.
Dan, I don't drink anymore.
I know. I drank for you. I drank enough out of both of us. So Dougal Dog had a question. He wants to know, does the dish have a parked position, or is it just last where it was stopped?
Well, the current position, actually, we're actually taking measurements at that position. Unlike a dish that is exposed to the elements, this dish is protected by a radome. We don't have any particular parking position, just wherever. Yeah. If it were an outdoor dish, then yes, we would have our parking position typically pointing straight up because that's the lowest wind profile.
And Cygnus has a question, and I know you covered this, but I have an expanded bit question on this. Is what's the dome made out of?
It's what they call a metal space frame dome. So the structure is steel, and the panels, the tent, it's really like a tent, is a fiberglass composite.
So what kind of attenuation does that offer, if any, with the metal framing and things like that? Does that cause any sort of interference or attenuation?
Not a lot. The dielectric loss of the membrane material is about somewhere about 0.035 to 0.4 dB at this frequency. At higher frequencies, it would be worse. And the space frame is interesting. If you think of a Faraday cage, when you're inside a Faraday cage, whether it leaks or not depends on the wavelength of transmission. So any structure that is considerably smaller than, let's say, about a quarter of a wavelength, the attenuation through that structure will be immense, right? But of course, the mean spacing of the structure here is like a couple of meters. So you can listen to FM broadcast radio up there. And it goes up high too. Like there used to be, when we first got here, there was a DBS satellite dish bolted to the main dish because the main dish never moved, and they used that for their TV feed. So it does work up to 12 gigahertz.
Well, I guess use what you have to.
Yeah, when we first arrived here, when we first arrived here, the dish hadn't moved in 25 years. So we got it going.
How much work did it take to get it unfrozen from that point?
Actually, one of the nice things about this dish compared to another one we restored or started to restore, because it's been under the radome all those years, all the mechanicals were in really good shape. So what we did was we manually unlocked the brakes, and there's this big wheel that you can turn to manually move the dish. And we did that, and it was fine. It was all, there was no grinding or hesitation or anything. So we knew that remotorizing it was going to be pretty easy.
So for those who don't know, the Reg Rhetoric, Boston Concerts, and the Drunk to Bunk Show are on their way to Florida right now, and they have joined us in chat after stopping for dinner. Apparently, Reds and Mike
thanks, guys.
are cuddling in the back of the camper right now, but they at least have us on in the background. I guess it's better than 70s music, but hey, I'll take it. Well, Marcus, let me first say thank you very much for the tour. I know when we first started talking about this, me going
welcome.
up there and streaming something very similar to what we just did for us to, for the channel and everything else. So I appreciate you saving me about a 5-hour drive, but it's still something I would like to do.
Well, you should come up anyway, obviously.
I would love to.
Yeah. Actually, the whole crew should come up. Like if Reds and Mike, and if they want to come up sometime, just let me know.
We can definitely make it a caravan of chaos again. Why not? We'll just do a couple different iterations of this. All right. I think that's all the questions we have right now for that. I guess so. So how long have you been at this facility? Have you guys been in charge of this facility?
I think about 4.5 years. We're just tenants here. Like it transitioned to private hands, like civilian hands back in 1999, I think. And there was a previous owner to the current owner that we, was here for most of the time, and then the new owner bought it about a year ago.
Perfect.
We're just the only tenants that had any plan of like what you were going to do with the dish. Oh,
well, yeah. Hey, at least it's getting used. That's all I got to say.
Yep.
Let's see. Did I miss anything here? You guys got to tag me if you guys have a question. Oh, someone's commenting about my shirt. Look, this is a Hawaiian shirt. It's just a little more subdued.
Oh, Oh, speaking of shirts. Let's see if we can
Not
see this.
stationary, I checked. Oh, I approve. That's perfect.
Yeah, there we go.
Yep. Very nice.
Yeah, if you guys have questions, by all means, tag me on them and we'll go through this. So without further ado, I guess we should probably go over to the thingamabob presentation.
Prezi.
Yeah, or Prezi here. I'm going to, hold on a second. Let me move Discord here. Blip.
And I tried to share my screen earlier. They couldn't get any more than a thumbnail out of it. So
All right, I'm going to share. Let's see. Nope, not sharing my email. I'm just going to share this screen. We'll share this screen here so that way you guys can see the presentation. There we go. All right, Marcus, do you see that okay?
I'm getting little blue circles. It's thinking about it.
Okay. About other panel members.
I see it. Okay.
Yeah, I can see it on. I've got the stream up on my other computer. I can see it.
No, it said stream failed to
You
start.
might have to put it on the. You might have to put it on your
the
laptop.
heck?
Then it'll just be a little bit of a delay.
Well, this is on
No,
my
I meant
laptop.
The YouTube channel on your laptop. 'Cause I'm sharing it on the screen for people.
Yeah. Oh, okay. Yes, I can see it. But there'll be a
Yeah.
delay compared to Discord, but we'll just
We'll
cope.
deal with it.
Okay. Oh, yeah, I can see it on YouTube. I just can't see it on Discord. Oh, and hang on. Okay.
Still with us, Marcus? Uh-oh. All right, Marcus, you good?
There's like this enormous delay.
Let's see. Well, if you want, you can pull it up on yours and we'll just start on the first slide. You can just tell me when to go to the next one from there.
Okay. Yeah, let me do it that way. Because if I have the YouTube and Discord at the same time, it's a
If
problem.
you have it up on your screen and I have it on
my
my screen, we're
Discord-
both on the same one. And then you can just say next and then and we'll go from there.
Okay,
Yeah,
so
on
I'm on.
mine, I got a new screen from DC that shows the stream, but I had to actually click on it to enable it. I don't know if that shows up for you, Marcus.
Yeah, you have to click watch
Yeah,
stream
I
on the
tried that, and
Discord.
all I got was the blue dots. Yeah.
Okay.
So I had the first slide here.
Yep. As your name and Dan Marlowe's.
Okay. Actually, the version that I'm showing doesn't have Dan Marlowe's name, but yeah. So you've already all met me, and you also know that I'm Patch Von Braun as well as Marcus Leach. So if you see me in side chats as Patch Von Braun, now you know who I am. And I'm with CCERA, as we've already discussed. Also, I want to go to the next slide, Dan. So I put up a note well slide because I want to emphasize that the observations we're showing here were conducted in a different context than debunking. They were conducted in the context of providing interesting data for our summer students to chew through. Now they have as a side effect showing all the things that we want to show, but we were motivated mostly by providing an interesting data set for our students, and as it happens, it's also a very decent data set to demonstrate the things we want to demonstrate in this context. So, lest people think we're spending a year to debunk flirts, that's not really how it went. Okay, next slide.
In other words, they're not worth the effort.
Well, yeah, not a year's worth of observations anyway. Okay, so the next slide is called 21 centimeter hydrogen emissions. Do you have that up?
Yeah, go ahead.
Okay, so way back in 1944, this guy called, I think it was Horst van der Hulst, postulated that this new type of what is called a ground state transition that actually Einstein and Fermi had worked on in the years before. They worked on the math of how it worked. His supervisor, Jan van Oort, sorry, who is, his name is associated with the Oort cloud. And Van der Hulst was a student at the time. He said, hey, student, why don't you see if there's any of these ground state transitions that Einstein and Fermi are yammering on about? See if there's any possibility that they might be something we could observe in deep space. So Van der Hulst went off and, looked at it for a while and said, yeah, I think the hydrogen transition is the most likely. Let's start looking for it. So Van Oort's team and a team led by Ewan and Purcell in the US started working on trying to observe it. Ewan and Purcell beat the Dutch team by a month or two, mostly because the Dutch team's receiver caught fire and they had to rebuild it. But after that, all of a sudden it was known that neutral hydrogen was well distributed in interstellar space. It's pretty much everywhere. And it's of a relatively high density. And when I say relatively high density, I'm talking, in standards of interstellar space. So the density varies anywhere from about 0.01 to 1 atom per cubic centimeter of space. So that's not much. That's harder than the hardest vacuum we could ever possibly produce down here on Earth. But there's enough of it, we can actually observe it. Now, if you look at the mechanism, sorry, I've just gone to the next slide. I keep forgetting. So the mechanism for the 21 centimeter emission, a neutral hydrogen atom is a very, very simple atom. It has a proton and an electron and nothing else. That electron, as it turns out, can be in one of two spin states with respect to the proton. So what happens is that the anti-parallel state is the lowest energy state, and the parallel state is a higher energy state. How they get into these states, it's they believe it's collisionally coupled. It doesn't happen very often. But the atom itself stays in that state for up to about 11 million years. So you'd think, well, if it's going to stay in this slightly higher ground state for 11 million years, we're never going to be able to observe it, except that there are trillions and trillions of these things along any line of sight that you might look at. So at any given time, there's just a whack of them flipping spin state and emitting a photon at 21 centimeters. Next slide. So, Doppler effect, which is how we measure the velocities of things that emit radio waves. The rest frequency of the hydrogen line is 1420.4-ish. Megahertz or 1.420 gigahertz with a wavelength of 21.11 centimeters. So the line, as you observe it from space, is not a narrow line. It's Doppler shifted and it's Doppler spread. So it's not like this very sharp line. It's more of a hump, and that's just because these emissions are not coherent. They're coming from a cloud. A big cloud, light years on a side type of thing. And not all of the atoms are moving in the same direction. So their observed velocity will be spread in a largely Gaussian manner. And their average velocity, if you took the average velocity of the entire cloud with respect to the observer, it will be Doppler shifted relative to its average velocity. So next slide. So we've already actually been upstairs to see the instrument, but I'll go over it again. 12.8 meter parabolic antenna, We have a dual polarization, 21 centimeter feed and low noise amplifiers. We have a multi-channel software-defined radio, which I pointed out when we were upstairs. Like I said, it's a former NATO SATCOM-2 station, and we began work in the spring of 2022, so about 4 years ago. And we achieved full operation with new motors late 2023, so not actually that long after we started up.
Yep, go ahead.
Next slide. So there should be a chart there or a graph, and that is just sample observations of the particular emission region that we were looking at for this entire year. And they're separated by, about 2 months. So over the course of 2 months, you can see that the spectral peaks here are shifted. It doesn't just stay in the same place. So why is that? Well, we'll get into that. And this is a radio spectrum, not an optical spectrum. So optical people may be a little bit weirded out by this, but on the x-axis, you have the redshift. The convention in radio astronomy is that a negative redshift is actually a blue shift. So this, for most of its time of the year, is moving towards us. And redshift is the other direction. Excuse me. So next slide. So we know that there's a Doppler shift. Why don't we just measure it every day and see what happens? So that's what we did. The schedule pressure on the dish this year was very low, so we could actually park it at the same location most of the time and take observations once a day. Excuse me. What will happen is that over time, if you plot the observed Doppler velocity versus time versus day, you'll see that a sinusoid will appear in that data. So what happens is that Earth's orbital motion modulates the nearly fixed differential velocity between the solar system and the observed region within the galactic plane. So the nearly fixed component consists of the radial velocity of the observed region and this in some indifference with the peculiar motion of the solar system towards Vega. For our purposes, we really only care about what I call the conceptual modulation, the sinusoid that appears, because conceptually Earth's orbit, if you think of it as a more or less constant signal, Earth's orbit imparts a very, very low rate modulation to the frequency of that signal. It's not really a signal in the sense that we think of telecom signals, but it's still a signal. Okay, next slide. So here there should be a nice long-term plot shown.
Yep.
Yep. Do you want to confirm that, Dan?
You have a long-term plot with that little gap in the middle.
Yeah. Yeah, you would home right in on that. Actually, let's talk about the gap first because it's really boring. The dish occasionally gets used for other things. And there was a 10-day interval back in the fall where that was the case. So we just didn't have data for those days, but it doesn't really matter. We have so much more data that the curve fits just fine. So the solid blue line, and again, I really apologize for the colorblind here. The solid blue line is the predicted Doppler velocity for that day, observing that particular region in the sky. And then the little X's, the little blue X's, are the actual observed data. And then corrected here is if you apply the what's called the VLSR correction to the observed data, you get more or less a straight line, which is the radial velocity of the object you're looking at. What you're basically doing is subtracting out the other velocity components to figure out what the sort of actual velocity is with respect to the solar system.
So it's basically getting down to like more of the raw, eliminating some of the raw data to get to the more refined data, correct?
Something like that. Yeah. Yeah. Basically what happens is that if you're making an observation of an object and you care about its Doppler velocity, you have to correct that velocity by today's VLSR correction, it's called. And that, of course, varies throughout the year because of Earth orbit. And it also, very frequently, you have to also apply what's called the peculiar motion of the solar system as a whole. It happens that these observations were made along a line of sight that was almost exactly perpendicular to our line of motion in what's called the peculiar motion. So we didn't have to care about that at all because it's effectively zero. So you can actually extract the actual radial velocity of the observed region directly without having to know the peculiar velocity of the solar system. Now, I've called this an algebraic analysis of the Doppler curve to distinguish it from the other analysis that I'm going to show you in a minute, because it really is very stupid and simple, and it's basically a little bit of algebra, not even algebra really. So the peak-to-peak velocity difference. If we go back to that plot, Dan. So if you look at the peak-to-peak, right? There's a peak at the top and a peak at the bottom. That's what we mean by peak to peak. So we'll go back to the next slide, to the algebraic analysis slide. So we measure that. We just, measure on the plot and go, oh, look, it's whatever. In this case, it was about 50 kilometers per second. And then you just divide it by 2. Because the Earth spends some of its time moving towards the object and some of its time moving away from it because of the nature of our orbit. And then, and this is a critical part, because if you divide 50 by 2, you get 25, which is not the orbital velocity, average orbital velocity of the Earth around the sun. It's almost, it's within like 10%, but it isn't quite right. The reason for that is that the observation is oblique to the line of movement of the Earth called the ecliptic. Astronomers know all about the plane of the ecliptic. So if you're making an observation that is off the plane of the ecliptic, you have to account for the fact that you're not observing Earth's orbital velocity directly. You're observing it off at an angle. And you can see this in real life all the time. If you are driving towards one of these radar speed signs that tell you how fast you're moving, their error gets very large as you get very close to them because the angle that they're seeing you at is oblique to the pointing of the beam. So the velocity, the apparent velocity just scales basically with that angle. So in our case, we just divide by the cosine of the ecliptic latitude of the observation, which basically just tells you how far off the ecliptic your observation is. And once you do that, you divide it and adjust it for the ecliptic, we get a velocity from our data of 29.8 kilometers per second. I'm sorry about my voice.
Take your time.
So the accepted values for the orbit from other people's observations over the decades is anywhere between 29.28 and 30.28. The reason it isn't perfectly uniform, of course, is that our orbit is ever so slightly elliptical. So it actually does vary by about a kilometer per second over the course of a year. But the average is 29.78 kilometers per second, and we got about 29.8.
Oh, it's pretty damn close.
So close enough for government work, I would say. And the virtual zero crossing is basically the middle between the two peaks. There's what I call a virtual zero crossing. in our case, because the peculiar motion doesn't have to be accounted for, we also get the velocity of the object itself of about, well, I call it an object. It's a region of hydrogen emission, and it's about minus 35 kilometers per second. So once you have an accurate velocity estimate, you can use other things you already know to estimate other things. Like, we know that a year is about 365.25 days. We know that. And we know that our apparent velocity is somewhere around 29.8 kilometers per second. And very, very simple math allows you to come up with an estimate for 1 AU of 149,672 and change kilometers, which is pretty damn close to the average distance to the sun. Of course, yes, our orbit is slightly elliptical, and if you look really closely at the sinusoid that we saw, it's not going to be a perfect sinusoid. But for purposes of quick valuation, are we insane? Yeah, we can just assume that it's a perfect circle. Now, once we know how far we are away from the star, we can then use simple Keplerian orbital mechanics in the simplified form, and we come up with a mass estimate for the sun. Because the Kepler elements in the simplified form, you're basically ignoring the mass of the Earth, because the mass of the primary gravitational object at the center of your little gravitational dance is so much larger than the Earth that basically Earth mass doesn't matter. So we calculated at the accepted value, and in fact, there's a little bit of disagreement about how heavy the sun is, but it's somewhere around 2 times 10 to the 30 kilograms, which is much more than you could, like, if you tried to buy that many Big Macs, you wouldn't succeed, even if you were Elon Musk.
Right. And like your bullet item says, you got within 1.5% of the accepted value.
Yeah, exactly.
Wow, this is pretty cool.
Now, there's also the Earth rotation question. It turns out that you can use the same science to get at least a notion that there's some Earth rotation happening. And what we did was, the students we had last summer, there were 10 teams, and they each built a little radio telescope, and they each collected 24-hour scan data at a fixed pointing. And then we picked sort of the best one, and Dan, my colleague, turned it into a heat map, which shows a distinct diurnal feature in the plotted data. And you can see it there. If you go to the next one,
yep,
there should be something labeled drift scan plot.
Yeah, I'm right with you.
Okay. The white line down the middle is just we just overlaid that to make it obvious. But if you take that away, you can see that there's a fairly bright region around 18 o'clock, and a bright region around 5 o'clock. And then there's just sort of this wispy stuff in the middle. So the bright parts are actually when you're pointing along the galactic plane, and you can imagine that there would be way more hydrogen if you're pointing along the galactic plane in either direction, as compared to when you're pointing more or less perpendicular to the plane. When you're pointing perpendicular to the plane, you're only pointing through about 500 light years of galaxy, whereas when you're pointing to to the galactic center, for example, around 18 o'clock, you're pointing at something like 40,000 light years of galaxy. So if you do one of these 24-hour plots and you do baseline correction, you can often see this structure in the data that has this 24-hour sinusoid in it. And that sinusoid is basically, actually, I'll go to the next slide because I think it explains this. So drift scan discussion. Yeah, so basically what happens is the beam, like you have a fixed pointing, the dish is just pointing somewhere in the sky, and it sweeps through a slice of the celestial sky every day. Earth is in what I call a local bubble of hydrogen emission, and the velocity distribution of that bubble is much smaller than the galaxy as a whole because it's all much, much closer to us. So it's not as if there's a... It's as if we're in this big sphere, and that sphere is emitting a signal. So it doesn't matter where we're pointing at the sphere, we see the same signal. And it's not like a really sharp signal, it has a velocity distribution, but that velocity distribution is small enough that you can actually see it as this ghostly thing in the Doppler data. So what's happening is that as the planet rotates, we're coupling, there's a coupling between our orbital velocity and the rotation of the Earth. Once a day, we end up pointing both towards and away from our direction of motion, and you can see that in the data. And that's what gives you that little, ghostly sinusoid in the drift scan data. And you should be able to overlay a couple of days worth anyway to reduce the noise because things don't shift that far in one day. And you should be able to make the Doppler ghost a little bit more obvious. And that's precisely the same as stacking in optical astronomy. It's exactly the same statistical tricks that are used. Okay, so we'll go to the next slide. And there's probably questions, but I don't know. Maybe we'll deal with them at the end. Yeah, we can deal with
them at the end. So far, I only got one that I was tagged in. So if you do have questions, make sure you tag me. I'm typing them up over here, so I can ask Marcus about it.
Okay. Sounds good. So this is the 21 centimeter observations. The nice thing about the 21 centimeter observations is that you don't need a $10 million radio observatory to make them. As I previously said, hydrogen is well distributed throughout much of the sky, and it's relatively bright in many, many locations in the sky. So you don't need a big dish. And there are hundreds of amateur radio astronomers all over the world. Now, granted, there are hundreds of thousands of amateur optical astronomers all over the world, so it's still a pretty small community. But this is something you can do yourself if you have a little bit of technical know-how and the will to do it. There's a website I put up, which is the umbrella organization for amateur radio astronomy. Earth orbit estimation will necessarily be of somewhat lower quality compared to our big dish, but not horrifically so. The main thing our dish has is spatial resolution, not sensitivity. Most of the hydrogen emissions in the sky are bright enough that it really doesn't matter. Like an amateur dish of a very modest size will be able to see it with adequate signal-to-noise ratio. And if people are interested, we can maybe have another talk that is focused on, okay, what do you need to buy and what do you need to do? Because I don't think we have time to do that today.
No, we can definitely do that.
Yeah, some other time. So one of the problems in using Doppler emissions to do this work is that you are inherently limited in precision. The reason for that is that the emission spikes, if you will, are fairly broad. So there's always measurement ambiguity, just trying to measure the peak in the emission. If it's broad, it's harder to get really repeatable, reliable results. Now, when I say really repeatable and reliable, I'm talking in terms of on the edges of doing new science. For amateurs, it doesn't really matter as much. And the other problem is that there's some spatial ambiguity as well. An emission region is large. So you never quite know exactly what you're pointing at. So that when you go and let's say you've recorded one particular spectral feature at the same spot in the sky every day for a year, you don't necessarily know exactly where that object is within your field of view, because of course radio telescopes don't form images. They're like data recorders, or 1 pixel imagers, if you will, or 1 pixel spectrometers, and the pixels are really big. So for us, not really doable for amateurs. There are strong absorption regions in the sky, which may be usable for us. Unfortunately, absorption regions aren't really observable for an amateur observer because they're very narrow and they're very spatially constrained. The one we're looking at the moment is M8, as I pointed out in the little update there, which is the Lagoon Nebula. What happens is the nebula absorbs some of the 21 centimeter radiation that is coming from behind it. So that means that you're observing something that is spatially constrained compared to other things you might be observing, and narrow in spectrum, which means there's less ambiguity in measuring the peak of the spectrum. In this case, it's an absorption peak, but it's still a peak. So we will get into more amateur stuff at the end of the talk. So the other thing we did was to take pulsar data that were already using for other reasons. We were seeing if we had enough of data quality to participate in something called nanograv, which is an exploration of gravitational waves observed through millisecond pulsars. And we wanted to understand both the tool chain and whether our overall data quality was enough to participate in that research. The jury's still out on that, to be honest. But when I started doing my hydrogen emission observations, literally right next door to the pulsar that my colleague was observing for an extended period, he basically said, hey, I think we can use the pulsar data to do the same thing that you're doing, but with much tighter constraints. So I said, oh yeah, let's do it. So we went over the data from about a year. Oh, also, Dan mentioned this earlier in the intro, but pulsars are really kind of interesting. They are really, really stable clocks, and this is just this happens because of their structure. They have insane amounts of angular momentum because they're the collapsed core of a star, and it collapses down to something the size of a small city. The angular momentum of the progenitor star is maintained. So they have insane angular momentum. They'll still be spinning at more or less the same speed thousands of years from now. So again, this part was not work I did. It was my colleague. He evaluated all of the Doppler data from the pulsar. This particular pulsar is the brightest pulsar in the Northern Hemisphere. And his method is curve fitting. You can see if you look at the, there should be a graph in front of you. Sorry, we switched to a new slide.
I'm with you. I read through this enough to where I knew kind of where your cutoffs are, so I'm going to keep it up.
Okay. All right, good. So again, the colors we chose were not friendly for those with color blindness, and I apologize. But you can see that the dots are the measurement, and there are lots of gaps in the measurement on this one. The reason for that is that pulsars experience something called scintillation. And I won't get into all of the details, but it's very similar actually to the kind of twinkling you get in the Earth's atmosphere, except that this is twinkling in the interstellar medium. The interstellar medium has weather. And pulsars actually are a good way to let you very roughly measure that weather, because pulsars are point sources, and so their emissions can actually get blinked out by the weather in the interstellar medium. And there are days when the pulsar is too weak due to scintillation for you to actually see it. So there's plenty of drops in this data, but Dan was able to use a curve fitting, it's a 4-parameter curve fitting model to fit model of Earth orbit to the data. And we got, I think, so you can see here, we got to within 1.00153 AU for our estimate. So whatever that is, 0.01% basically. The eccentricity, which the standard eccentricity is 0.0167, we were able to derive 0.016694, which is pretty darn close. And perihelion, we got fairly close. Perigee, we got to within 31 minutes over the course of a year. I think that's pretty good. How many minutes are there in a year? A bunch of them. So yeah. The other thing that
I was going to say,
go ahead.
I want to talk about real quick on this is what's the 28-day cosine of residual on that?
Well, we'll go into that on the next slide, I think. Yeah.
Sorry. Dog barked.
Yeah, no worries. So in the analysis of this, so pulsars have an apparent timing. And the apparent timing of a pulsar is affected by annual Doppler effects, just like anything else would be. You can notice this. Trains used to use a bell. They'd go ding, 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 ding at a pretty regular cadence, and as they passed by, the apparent cadence of the bell would change. Not just the frequency of the note that the bell was playing, but the apparent cadence would change slightly as well, and you could actually notice it. This is the same thing. So a pulsar produces a pulse at a very regular interval. The observation of that is subject to Doppler effects. So what you do is you measure the time of arrival deviation from what you would expect, and you use that as your observable, basically. And you can see, again, you can see a sinusoid in the data because of Earth orbit. The particular pulsar we're using, it's got a notional period of about 0.7145 seconds. The effects are tiny, but we have a really, really good system clock. It's actually better than 0.1 parts per billion.
Wow.
Which allows us to do long-term measurements of these sorts of things. You generally, when you're doing pulsar observing, you need a really good clock anyway, even if you aren't doing this particular thing, because the way you detect pulsars requires that you overlay a bunch of pulses one on top of another, because they're very weak. So the only way you're going to see them is if you do what amounts to stacking, like they do in optical astronomy, except this is stacking that is time synchronous. You stack over exactly one period of the pulsar, and you may stack 50, 60, or 100 pulses together just to be able to see the profile of a single pulse. Now, there are exceptions. If you have a really, really big dish and a really bright pulsar, you can actually see individual pulses without stacking, but most of the time you need to use stacking. Or synchronous detection is what they call it in radio. Yep. Okay, so the next slide is talking about the curve fit. Well, I think I covered a lot of this. So it's a 4-parameter fit. Sparse data, as I discussed, and we were able to derive the eccentricity to 0.036%.
It's amazing.
And again, like I said, we derived it to within 31 minutes on January 4th, 2025. Now, okay, getting to the fun stuff of this. When we extracted the residual from the data, which basically means we take the data and we subtract out the curve that we generated, we got a 28-day periodic feature in the residual. And we scratched our heads, and then we did a bit of research, and it turns out that if you have sensitive enough observations and a stable enough system, you can see the effect of the moon on Earth's orbit. It imparts about a 10 meter per second wobble in Earth's orbit over a 28-day period, and that's what we were seeing in the residual. Now, I'm not going to say that amateurs are going to be able to do that unless they're very well heeled. But we saw it because we have really good clocks and a relatively sensitive instrument. And at first, of course, we were both really surprised. And then we're like, okay, this actually makes sense because the Earth-Moon system, the barycenter of the Earth-Moon system is actually below the Earth's surface, but it's not right at the core of the Earth. And this shouldn't be a surprise because we have this moon, which has non-zero mass. So if you look at the system as a whole, the gravitational center of the Earth-Moon system is actually, it's not quite at the core. It's like, 70% of the way to the core or something like that. I don't have the numbers off the top of my head. But because the moon rotates around the Earth, it's wobbling. The apparent velocity wobbles. Okay, next slide. Amateur pulsar measurement. I'm going to touch on this briefly because amateur pulsar observing is not impossible. It just requires more money and more dedication. I know a number of amateurs who have observed various pulsars. It just requires a larger investment in receiver equipment and a dish that's at least 3 to 4 meters. You'd have to operate at much lower frequencies where pulsars are brighter. And there's much larger potential for radio interference. You need a good clock source, but GPSDOs, they're like GPS-based high precision clock sources, basically. They're not that expensive these days. They basically take advantage of the fact that GPS is a clock. At its core, GPS is just a clock. So what you're doing is you're steering a local clock on the ground to GPS's clocks, and you're able to achieve 0.1 to 0.01 parts per billion with even a relatively cheap GPSDO these days. You'd need to observe for longer, so you'd end up with more measurement ambiguity. And the only pulsar you can observe with a dish of 4 meters is the one that we've been observing. It's the brightest in the northern hemisphere. There's another really bright one in the southern hemisphere called the Vela pulsar. But really, there's only 2 on the entire planet that are bright enough for an amateur-sized dish to observe. And again, if people are interested in that and they're really serious, they can contact me and we can talk. So future experiments here, we may be able to use OH maser emissions. So some stars are what they call evolved stars, and they have an envelope of gas and dust around them. And the energy from the core star actually is enough to cause masering in the envelope. And that masering very often happens in the hydroxyl maser emission lines. So we have a small dish outside that's pointed at this bright maser called V669 Cassiopeia. And it has an emission line at 1612.231 megahertz. So it's spatially compact. These maser regions on the shell or the envelope of these evolved stars are quite small relative to other things you might observe, and they're very spectrally narrow. So perfect, absolutely perfect for doing high precision Earth orbit monitoring. And we think we can get away with using a much smaller dish to do it. So we've dedicated a dish just outside the door to do this, and we're almost ready to start doing that. Again, this is something that an amateur could do. They could spend a year observing the maser emissions from one of these bright maser regions and doing the analysis, and probably actually coming up with, assuming they have a really good clock source, coming up with a very, very good estimate of Earth orbit. So I think I mentioned, we've moved the dish to M8, the Lagoon Nebula, and we'll be doing both 24-hour observing runs to allow us to estimate the value of the peculiar motion, which is what I talked about earlier. There haven't been a lot of people doing this in the radio domain.
No, I did. You're at the
guys?
last slide, so I brought everybody else back on board.
Gotcha. Okay. So the original estimates of the peculiar motion in the astrophysics community were accomplished with both 21-centimeter observations and optical observations. But since then, which is decades ago now, there hasn't been a lot of extra work in that. And I think it's an interesting thing to explore, producing possibly refined estimates for the peculiar motion of the solar system.
So I do have a couple of questions, and I'm sure this particular panel has questions too. So let me ask the one from chat first, and then I'll kind of let the panel go wild at their leisure here. So the one question we had was from the Copium Emporium, and he wanted to know, how do we discover the hydrogen electron spin flip?
Well, actually, that's a really good question. So Einstein and Fermi basically postulated the existence of all of these really interesting ground state transitions, and they came up with some mathematics to basically predict them. So the hydrogen one was at 21.11 centimeters. There are plenty of others. But the first time we actually observed this was in interstellar space. And then later, we started producing hydrogen masers in laboratories that basically reproduce this effect. But also, so that the best synthetic clock sources in the world at the moment are hydrogen masers. They're very, have very, very good short-term stability, like 1 part in 10 to the 16 over like a few hours. They decay a little bit, like I think 2 orders of magnitude over a longer time period. Over short time periods, they're really, really good. But no, the first time we actually observed this emission was from space, and then we figured out how to do it in the laboratory.
Astro, you got one?
Yeah. I had a quick question for Marcus. Referring to the peculiar motion, is that conceptually the same as Earth's motion, or really the solar system's motion, relative to the local standard of rest?
Correct. Yes.
Okay.
Yes. Yeah. When you do what's called a VLSR correction, what it's basically doing is computing the projected peculiar motion and Earth orbit as a combined correction to whatever your observation is.
I see. Yeah. I think it's very so it's basically just slight differences in terminology. I'm hearing peculiar motion, but really it's about the solar system local relative to the local standard of rest, which we refer to in optical astronomy quite often, which is essentially the average motion of this entire region of the galaxy. So you kind of average that out, and you figure out what the local standard of rest is and how we're moving relative to that.
Yeah, the problem is, of course, that the galaxy is a big and complicated place in terms of motions. So, when you're trying to measure the velocities of things, you have to go, okay, what is the rest frame for that? And the local, collection of background stars, as it were, is called the local standard of rest, and that's kind of like the local rest frame, and everything gets measured against that. I don't even know how you would do it, like, globally.
Right.
Because the galaxy is big, and motions become more and more complicated. Like, we like to make fun of certain science denier types for their inability to do 3D spatial reasoning. Once, even as somebody who is fairly comfortable with it, getting into all of these different motions that are involved, it actually causes you to scratch your head. Even as somebody who kind of does this, you have to think about it. Well, okay, so what does that mean? Oh yeah, I need to take the projected velocity here. Well, what is that velocity projected velocity relative to, all of that kind of stuff. Even the projected velocity relative to the ecliptic is something that doesn't immediately leap out at you until you think about it.
And to expand upon that too, because I mean, you're talking about the fact that the idea that the moon caused this, this odd change, it wasn't real apparent off the top of your head because you're trying to, obviously account for all these different motions and all these different, spatial constructs that the moon is very close and, interstellarly speaking, and it seems pretty obvious, but it was still a surprise.
Yeah, and it's you don't think about it until you are forced to think about it. It's obvious once you know what's going on. It's like blindingly obvious. But the effect is quite small, 10 to 11 meters per second, which if you're doing gross measurements of the Earth's orbit, which is, ballpark 30 kilometers per second, a little tiny error of 10 to 11 meters per second is probably not going to bother you that much. But when it leaps out of the data at you and hits you over the head, you go, "Wow, that is so cool."
Definitely.
Yeah, I mean, it's a testament to how accurate your measurements are, right? Like, when I was doing my velocity aberration measurements, I was just looking for a signal. I wasn't trying to come up with, here's the exact value of Earth's velocity. I was trying to see, is it having a measurable impact on the size of the image? And if you look up my data, like in terms of the dot plot, like it's significant, but there's some overlap there in the data points at the extremes because I don't have that level of accuracy with velocity aberration measurement. It's a tiny effect. So the fact that you're able to detect that, doesn't that also imply that if you measure the moon's orbit, its distance, that you can actually come up with the actual mass of the moon from those data, or at least get an estimate?
Actually, yes, you should be able to do that. You should be able to throw a few little Kepler equations against the perturbation that we've observed in radio, and you probably can come up with an estimate.
Mm-hmm.
In amateur radio, when you do moon bounce, you can actually detect some of the Doppler shift from the moon's libration and nutation.
Yes.
You always have to account for that and everything else if you're trying to do EME or whatever reason.
Yes, we will be doing EME here at some point. It's taken more years than we thought it would, but there's only so many projects we can execute at a time.
And there's also, obviously better days than not to do that. So usually there's a forecasted kind of a thing for that. So quick question on the EME though. You guys are looking to receive your same signal, correct? So if that's the case, do you want to try to time it to basically say it takes, like I did it when I did it. I used an 1950s oscilloscope. And I was able to measure what the time frame is, and then from that, I was able. Obviously, it was not very, what's the word I'm looking for? Accurate. Like to multiple decimal points. It was like to 2. So I was able to derive that. But I'm sure with the size of the antenna and the instruments you guys have, you guys will probably be able to get something a little more accurate than that.
Yeah, we will probably have to deviate from the usual ham radio protocols for EME because I don't think any of them have precision timestamping in them. So you'd have to come up with something that has an embedded precision timestamp, send it, receive it back, and compute the time delta. And you should be able to get a very good estimate. You'd have to estimate the instrumental delay as well, but that should be easy to do.
So one of the things about having a GPSDO is that, of course, you can connect it to the SDR, and you can go off the phase of the signal going out and just use that as the timing.
Yes, that's true.
Yeah,
it's true. Yep. Yeah, well, the EME project here is making slow progress. Unlike an amateur scale dish, it's not like you can wander into the backyard and get up on a ladder and start changing things at the feed. We have to assemble a complete scaffolding setup, which takes probably a couple of hours with all of us involved, and I'm the youngest of the geezers involved here, so it's it's a physical challenge. Then you have to climb up the scaffolding and do whatever you do, and it's a major deal, and we don't like to do it very often.
So I think of the people that we have here, yourself excluded, Marcus, because you obviously have a very large play toy that we don't have. Astro has been working with a 3-meter solar cooker, right?
Yeah, I ripped the reflective material off my purchased solar cooker to produce a reasonable approximation of a dish, which I still need to work on some more. I need to modify this thing some more. I got to chop off, I don't know if you can see it, but I got a picture of it here. And there's a stick that's coming up out of the center of the dish. That needs to get cut off. Also, my arms for the secondary are basically just drywall corners that I got at Ace Hardware and slapped in there because I purchased one that was designed as a solar cooker. Save It for Parts has a very similar dish, but his actually came with a proper feed because it was designed to be used in that for that use case. Mine was definitely not. So I'm working on trying to get this up to snuff so that it isn't just tied together with bungee cords as it currently is.
Well, Save It for Parts will appreciate that because that's kind of right up your alley, right, Gabe? Now you obviously have an antenna farm of sorts, and you're working on. You actually have your own radome as well and your own antenna, correct?
Yeah, and that is thanks to Marcus. He actually saw my channel and invited me up to the observatory there and said, "Hey, we've got a dish, a radome here, kind of sitting in our scrap pile, and some reflectors as well." So I went up there with we got a U-Haul truck, and we went home with almost, I think it was it's something like 1.9 radomes is what we ended up with in spare parts. Yeah. And then we haven't put up the second one. We haven't quite figured out if we have enough parts to do the second one, but I think we have most of it. But yeah, I have a very similar dish. I believe mine's only I don't think in meters very much. We're here in America, so I use Freedom units, so it's about a 7-foot reflector, but it's similar to the solar cooker. Was sold as a C-band satellite dish. And so I have that in the radome currently on just a security camera pan tilt mount. And Marcus actually also sent me some motor systems to try to make a bigger mount for a bigger dish, which I'm still working on. I'm not great at actually engineering things from scratch. I'm much better at finding stuff in the trash and kind of forcing it to do what I want, like a security camera mount has become the dish rotor system. But much more, have been focusing much more on satellites, but I'd like to do more radio astronomy. A lot of Marcus's math and graphs are a little over my head, but I'm hoping to learn more about how to do some science with it.
So
I will point out that the Society of Amateur Radio Astronomers does have like a kit that they sell. Fundraising for the organization called Scope in a Box. And it's a small paragrid dishy thing. I'll leave it at that. A feed assembly, low noise amplifier, a little SDR receiver, and some software that they put together so that you can basically, throw it up in your backyard and start taking some measurements. Obviously, for this work, you'd need some analysis tools as well. But in terms of like really simple, small hardware just to get started, that might be an option for some people.
So Marcus, I also had a question about the analysis tools you mentioned there. And a question that I had in my head was looking at your data, looking at the drift scan data, would it be informative to look at that over the period of a year and sort of animate that to see how it changes as we go around the sun?
Actually, I did that years ago. I did this long-term animated GIF of FFT plots. I think I only did it over a day, but doing it over a year would also be really interesting. And maybe animating the highlights or something. And what we're hoping to do, like the dish is currently pointed at M8, and we take a daily observation just specifically of M8, but we're also doing 24-hour drift scans, try and get a good enough signal to noise ratio on, what I call the Doppler ghost, to allow us to estimate the peculiar motion. And whether we succeed or not, I don't know, but we think it should be possible.
Oh, that'd be really interesting. Yeah.
I had a question, Marcus, as well. So you had mentioned earlier that it's kind of difficult to get an image, get more of an image with a single pixel radio telescope, and that's something I've done a little bit with on the field of satellite stuff. I've used what I called a miniature radio telescope that basically did I incremented through an azimuth and elevation range and just recorded a signal at each pixel.
Yep.
And I was mostly imaging geostationary satellites, and that's something that can be done on the order of a second or less at each position. And I'm interested in trying to do that with things like the hydrogen line, with things like radio astronomy frequencies, but I'm under the impression that it takes much more integration time at each position, that you have to kind of sit and record your signal and then get kind of a baseline. But maybe that's maybe I'm wrong about that.
It really depends on what kind of science you're trying to extract from the data. If you're just doing spectral work, you really only need tens of seconds at any given location. You'll miss some stuff because your integration time isn't long enough, but you can get a really rough sky map just by doing that. If you have the ability to move to any arbitrary location, integrate for 10, 20, 30 seconds, take the spectrum, move on, and then collate all of that data organized by right ascension and declination, then you end up with a sky map. There's a paper on our website about something similar we did, I don't know, 6 or 7 years ago, where we produced a sky map of 21 centimeter brightness from, I think the lowest declination was about -20, and the highest declination was about +70, something like that. And we produced a sky map. It took us a while because we didn't have an instrument that could scan in both directions. So it was basically a meridian transit type instrument where we just incremented it by a couple of degrees every day. And then we redid all of that 2 or 3 times to get enough data quality to produce a map. But that's definitely the kind of experiment you could do. I'll point you to the paper. The math is not that hard. It's pretty straightforward stuff.
Sure. And then I guess my other question was in regards to relative motion of different systems. Then if you're doing one of these scans over, let's say, if I'm doing a scan like this where I'm incrementing the dish through a bunch of positions, I will probably need to also factor in the Earth's rotation and other motion effects of that.
I mean, yes and no. It depends on what kind of science you're trying to extract from the data. Earth motion is inherently encoded in things like right ascension, because right ascension tells you what local mean sidereal time it will be when that object crosses your meridian. And of course, Earth motion is, 2 motions are actually involved in that. One is Earth motion, and the other is orbital motion. And the reason that sidereal time gets 4 minutes or so earlier every day is that we are in orbit around the sun, so the positions of things will shift. But if you're collating things by right ascension and declination, at least part of that will get factored out.
Okay, yeah, and see, as a relative newcomer to this, I don't think in terms of the astronomical positioning system as much. I think in azimuth elevation because that's more related to satellites. So these are kind of some new things that I'm learning about.
Yeah, once you really get your head around right ascension and declination, it's the time base against which the stars, or it's the time base that describes the motion of the stars, basically.
So in terms of replicating what you've done with 21 centimeter observations, how critical is it to have any kind of tracking, or do you think a stationary mount would be sufficient to get reasonable accuracy.
Yeah, no. I mean, you have to have patience, obviously, because you need to. I mean, ideally, you need to do this for a year. But if you did it for 6.5 months, there'd be enough of a sinusoid that you could say, "Okay, it's a sinusoid. Come on." And no, you don't need a tracking dish. Like if you like what we did with our big, expensive $10 million dish here is we parked it. We parked it at a single meridian pointing for more or less an entire year, except for other things in the schedule, and just took recordings once a day. The same thing could be done with an amateur dish. And if you have a lot of amateur scale dishes like Gabe has, you just set one up and dedicate it to that task. And after a year or whatever, you'd have enough data to do the analysis.
So,
yeah, that sounds perfect.
So Astro K, I would just like you to thank the cat for mooning us on screen. Appreciate that as he reset himself to be your first stole and keep your neck warm.
The cat does.
Cats do cat things. They're all there is.
The cat does what the cat does. Yeah.
Yes. Sorry about the cat.
I had a couple of cats that would do that. They were just the sweetest things. My current cat doesn't. He's not as cuddly as other cats I've had. But
yeah. I got a super chat. Basil problem. I greatly appreciate the super chat. However, it's not relevant to tonight's conversation pertaining to whether or not Craig has a nuclear engineering degree. I'm happy to have that conversation. It seems to be having it during chat with people more knowledgeable than me. If that's something you would like to talk offline, we can have a conversation offline. You can reach me on Discord. Otherwise, thank you for the super chat and supporting the channel. But that topic generally not part of this, so I'm going to skip it for now. Hope you don't mind. Anybody else in the chat have questions that they want to ask of Marcus and this experiment and anything else? Feel free to tag me in them. Otherwise, I had to turn on my light because it progressively got darker very quickly. And next thing I knew, I was in a shadow. I wasn't paying attention. So apologize for that. Anybody else on the panel have any other comments or questions for Marcus pertaining to this, or things in the future, or just thoughts in general about what they thought of this? I mean, for me personally, I thought it was a very novel idea, applying it in such a way. Marcus and I have talked, at length about this, and I know he said that this was originally done in 1944, and there was there's two teams that ended up going to do it, but it was through a different application. So I still think that this application was great for, like you said, the garage scientists, the sort of what people can do. But at the same time, it kind of alleviates that whole talking point of someone reading relativity and saying that, we can't do a terrestrial experiment to, derive the orbit of the Earth. But the funny thing about that is that was also written in 1901, and we are now in 2026, so we have various different things that we can do. One question I do have,
well, one of the
something
things
that I actually have two of these. Amateur radio astronomy is very niche. Amateur optical astronomy obviously has a little bit of a bigger foothold, to say the least. And there are some, like Astronomy Live, who are willing to obviously cross those paths and things like that. So what do you think is the ceiling for amateur radio astronomy? And obviously it's going to be starting with dish size, but
I would say that would be the dominant factor in terms of expenditure. There are only a handful of amateur radio astronomers on the planet with significant sized dishes. There was a guy, and I don't know for sure, but I think he might have passed on, a 30-foot dish in New Mexico. And he was using some software I wrote for him, custom, I don't know, like 10 years ago. He was able to observe about a dozen different pulsars in the Northern Hemisphere with that dish. That was his main thing. Like, he didn't care about anything else. It was just, for him, it was like some people collect dolls. He collected pulsars. Like, that was his thing. And I'm like, oh, okay, Joe, knock yourself out. And And there are other organizations similar to ours that happen to find themselves with a big dish, but it's mostly amateurs. Like, I mean, yeah, I do some things that might seem like professional astronomy and astrophysics, but really at my core, I'm an amateur. So there's the Deep Space Exploration Society in Colorado. Actually, I don't know if CK is on the side chat or not, but they have I think it's a 18-meter dish in the middle of Colorado somewhere, like middle of nowhere. They had to get power pulled in and all this stuff, and they do some interesting work. I can't think of another one in North America right now. There's also an outfit in Germany called Astropylar Stockert, and they have a 26-meter dish.
Your German's terrible.
That they basically inherit. My German is terrible. Oh well.
There's a group called the Titan Observatory, which I think they just bought a dish on Craigslist down in Florida, and I'm trying to find them. I'm on their Discord, and I don't know all the details on that, but I think that is another one that's starting.
Astronomer's going to get off this and go talk to the wife.
They scored.
We need more land.
They scored a 9-meter dish, I think, but they have to move it, and that's the main thing. They have to move it to. They do have a site that they purchased or they've got a long-term lease on that they're going to move it to.
Right.
So yeah.
So one of the cool things that you can do at these low frequencies, 1.4 gigahertz, is if you have very precise timing, you can take a bunch of smaller telescopes or a bunch of smaller receivers and time them together to make essentially a larger one, and that might be more doable for a amateur to do, and that might be something I want to look into.
Actually, while you bring that up, Kate,
I'm
can you show us? Did you print your horn already?
Yes, well, parts of it. So I have a day job, and I've had no time. But this is part of the horn of the antenna I'm building. Let me actually share my screen so I can show people what I'm working on.
This is to do this sort of experiment, correctly?
Right. So the big thing that science deniers will say, at least that I predicted, is that Marcus has government equipment. He has millions of dollars equipment. We can't do this ourselves. So I decided I'm going to build a radio telescope myself. Using nothing but a 3D printer and tape and good old engineering. Share my screen. I'm going to share my
as
full
she
screen.
pulls this up, as we get ready for this to pop up here, there was actually a conversation going on between Astro Kate and Marcus, and I just sat back and watched and felt like a knuckle dragger as they were discussing this horn and the different aspects of it. So it was a quite humbling experience for those who haven't been there or around those kind of conversations.
Right. So the first thing that I had to do was sort of design the parameters. So I created this Jupyter notebook, which is just if you don't know what that is, it's just a Python file with some extra steps involved, and you can see the outputs. And so the interesting thing is that, of course, I plot it all out, and I say, if I want, to receive this frequency, here's what I roughly have to do based on, textbooks, that kind of stuff. If you want to do a horn antenna. But then what I do at the bottom here, I know it's hard to see all this gobbledygook, but I run EM simulations using software called OpenEMS, and I get these graphs out. And these are really cool. If you've done any sort of radio engineering before, what you can do is actually see how this would perform in virtual space. So what I'm looking at right now is something that I might see on a VNA, a vector network analyzer, which is a very RF-centric piece of equipment. But right here we have the VSWR, the return rate, basically, like how tuned it is. So we can see it's just around the 1.4 gigahertz hydrogen line. And here is something that's really cool. This is the feed point impedance. We have both the real and imaginary. And if you know what a Smith chart is, and I realize that many people in the audience might not know what a Smith chart is, but that's basically how we measure how well an antenna is going to work. we see that it has about 50 ohms of real impedance at about 1.4 gigahertz and about 0 ohms of imaginary impedance at the same frequency, which means it's like perfectly tuned. On a Smith chart, the 50 ohms would be right in the sweet spot in the center, and then the imaginary line here would be the capacitance or the inductance in the antenna. Don't worry, I know that's a bunch of gobbledygook engineering stuff. And then down here, of course, is the antenna pattern, which you can actually send out the EM fields, EM waves, model it, and see what it looks like. And it's not great, but it'll work. And so you can see here, I have a little virtual machine full of wonderful things. This is the model that the code generated, that it calculates the EM fields from. And you can actually take the output of that and put that into something called ParaView and actually view the output as it's generating signals. So you can imagine the horns facing, towards the screen here, and you can see the EM waves radiating away, and we can see how that works. And then the other thing I think I should show is my regular setup. So I'm printing this out, but I do want to point out that I do have this out in my balcony, which is a fully rotatable hobbyist setup with a 3D printed feed. And this will do every frequency from VH up and higher, from Earth to space, up to about geostationary orbit. And this dish itself was salvaged from a cell phone feed, essentially. So I have all these things that I can throw together. And when work is not kicking my ass, I will make sure to have a bunch of completed projects for everyone.
Yeah, people like Kate and I are confined by the amount of space that we have available, being that we live in apartments. So,
yeah, I was looking at the housing market around here, and it's ridiculous. My studio, my studio is already ridiculously expensive, like $3,500 a month for a studio apartment. And I was looking at what it would cost us monthly just to own a home, right? And it would jump up to over $12,000 a month of just taxes and everything. And it's like,
I got a super chat here from Red's Rhetoric saying that they're in my driveway. Let's go. So apparently they're here to pick me up, even though I told them I can't go. Despite the guilt trip from Red's Rhetoric last night, that took over an hour and a half of him trying to guilt me into going to Florida with them. So as much as I would like to have been down there, and especially to go hang out with Astronomy Live and the Drunk the Bunk Show, Red's Rhetoric, and Boston Concerts, and all the other content creators between here and there, sorry, not able to go. I have some corporate overlord taking over soon, so I'm required to do some stuff. So that should be relatively soon. So we'll see how that shakes out. But unfortunately, that's also why we don't have a lot of content going on right now, because I'm spending 2 hours on a train one way to go to New York City to go sit on stuff that I don't need to sit on. So go figure. Such as our normal day jobs that require some sort of things for us to do so we continue to get paid, as we can pay bills. I'm unfortunately not able to turn YouTube into a income stream per se, nor do I necessarily want to, because I'm not that creative, and I'm definitely not that good at editing. So, well, I tell you what, I don't see any more questions going on per se. Let's see. There's another side conversation on here I'm going to take care of here in a minute, depending which direction it goes. So without any more of questions from our illustrious audience here, I'll turn it over to final thoughts for you all. I'm going to take a page from Max's books here. And since we start with Astro Kate with our introductions, because of course, ladies first, she gets to go again.
Well, I look forward to doing this. This really sparked my journey into doing radio astronomy. I've been doing optical astronomy for quite a while, and also radio work for quite a while. I don't know why I haven't put the two together until now, but I look forward to it. And this is something that amateurs absolutely can do. I will warn you that getting into radio is not as easy as I thought it would be. So I started doing RF engineering several years ago and deep diving into it. And I thought it was just as easy as create a digital circuit, slap an antenna on it, and you're done. That is not the case at all. But it is absolutely something that anyone can do and get involved in, and I would encourage them to do it. There's a great community already. The amateur radio astronomers are out there and talking to each other and giving tips. And so, yeah, thank you so much for, getting me involved in this, because I really need to start doing this.
And thank you for showing up and being part of the panel. I greatly appreciate it, Kate. Thank you. Gabe, let's go to you.
Yeah, likewise. I'm really learning a lot, and I'm learning how much more I have to learn about getting into the radio astronomy hobby. Which, yeah, again, I've been in radio. I've dabbled in optical astronomy, and that's something else I'd like to do more with. But yeah, this was a lot of fun, and it's really got some new directions for me to look at for some of my hobbies.
All right, Astro, you get to bring up the rear, so to speak.
Well, I thank Marcus for getting me into this, getting into radio astronomy and radio in general. I've been, purely optical amateur astronomy for years now, and looking forward to delving into this. And I thank Marcus for his patience as I pick his brain on things like feed design for the dish and all of that. I actually want to pick his brain offline too about these potential maser observations of OH radicals. That looks really interesting. I want to see what what we might be able to get out of that too. But yeah, I'm looking forward to starting some 21 centimeter observations. So it's been a while since I've been able to upload to my channel too. I've had a lot going on, both professionally and debate wise. But hoping to generate some content with both Artemis 2 coming up, optically tracking that, but also getting into 21 centimeter observations. And yeah. Parking the dish for a year in my yard and grabbing some observations and seeing what we see with Earth orbital velocity, hoping to replicate what Marcus has already done a great job doing.
And definitely, and I'm excited, for you three as well, because I have to live vicariously through you. Because I can't really put a 3-meter dish anywhere where I'm at unless it's going to be on a trailer that I park out in the parking lot. And well, the management company at my apartment complex probably is not going to appreciate that too much per se. But I'm interested to see what you guys all have. We'll revisit this and see what kind of we can show that absolutely you can do this, and it's not just a theory kind of a thing, because we have others that do it. For my final thought, and then I'll have Marcus kind of close everything out. Radio astronomy is like radio. It seems sort of easy, and as Astro Kate alluded to, it's not. There's a lot of engineering and details and nuance that kind of goes into things. But if you do want to get into it, there's people out there who are more than willing to help, and they're more than willing to lend their expertise. People like Astro Kate, people like Astronomy Live, people like Save It for Parts, people like Marcus, who are willing to share our passions with you. So if it's something that you want to get into, you can always reach out either to me directly and I can put you in contact with people, or you can reach out to them directly, because most of them already have a channel and they have contact information on them. I have one question for you, Marcus, and I'll let you have a final thoughts. Is this, and I wrote this out earlier because it was kind of pertinent to me as a dad. What would you most want a curious 12-year-old who may be watching this, because for the first time I've watched my language the entire stream. If they're watching this, what would you want them to take away from that, do you think?
I think that I would want them to take away the fact that this is doable by anybody with the right motivation and a little bit of background. Like I said, we had a summer school. We hold summer school here for 12 to 16-year-olds, and most of them are quite successful in the simple experiments that they work on. And I mean, it's stuff that a motivated 12-year-old could do. Absolutely.
And to be fair, and one thing I would tell that same 12-year-old is that optical is great. and I'm sorry I'm going to dump all over you here, Astro, for a minute. Optical astronomy is great, and it provides some great pictures. But the universe as a whole is not just one wavelength or one small band of wavelengths. It's an entire bandwidth, and you learn and discover so many other things by going into those ones that maybe you don't see, but you can see them in plots, you can see them in graphs, and you can see them in waterfalls and things like that. And while different, it still accomplishes something. And I think that's something that just as a whole, from my own RF experience, my own RF engineering, it's, you know, is always based on communications. I see this as something, I'm used to more of a transmit and receive sort of end. This is receive only. So it's something that I definitely appreciate the amount of engineering that goes into it. And I'm, like I said, I've been been part of this chat for a couple of months now, I think, and this group chat that we've had and there's discussions in them. And I've learned immensely a lot from these, from this collection of 4 people here. And I probably continue to learn. But if it is something you want to do, by all means, I think you are surrounded by quite an expert panel that is more than willing to help. So with that being said, if you do want to get into it and you do it, drop me a line and let me know, because I would like to have a running total of people who are doing it, because we can all take all the results and match them together, and we can throw it on Marcus and say, what does this mean? And and he can help us, because you know, it's, as with all engineering, there's specializations and things like that. So while I can maybe design a transmit and receive circuit for a ship, you know, in the middle of the ocean, doesn't mean I know what the hell I'm looking at just because I point a dish at the sky. So that's why I rely on people like Marcus and stuff like that to be able to help out. I do have a question from Bruce Wayne and Astro. I think this is going to be directed to you. Do you think the court will accept the Artemis 2 launch as an excuse to skip jury duty? Only if you're on it, I think.
Yeah, I was going to say, if you're out of the country because you're in space, maybe.
Yeah, I think that's the only way that you're going to be able to get out of that, Bruce Wayne. I'm sorry to tell you. Digital to RF, so chalk and cheese.
During the Apollo era.
Well, I tell you what, Marcus, I'll turn this over to you as far as any final thoughts, but I would like to say thank you very much for presenting this, and thank you again for presenting this all to us and taking time to not only give us a tour, which is something that we talked about, but also to explain this. It's something I really wanted to kind of get on the schedule, something I really wanted to talk about because I found it very fascinating, and I think it was the perfect thing for me to kind of launch into this whole citizen scientist kind of thing that we're going to start doing here on the channel. So it'll be a little sparingly. I don't think it'll be very regular, but there are some, the funny thing is Marcus and I have already talked about a couple of different experiments to do for this, whether it's muon detection with cameras or whatever. There's a couple of other different things that we're going to be doing. So with Marcus, I turn this over to you.
Sure. Thanks, Dan. It's been a lot of fun, and I hope people enjoyed the tour and the talk and all of that stuff. Sorry, the Prezi. I hope they enjoyed the Prezi. I have to say, I've been doing electronics and radio astronomy more or less since the mid-1980s, on and off, and I still learn stuff. There's still lots of stuff to learn. It's not a static field by any stretch of the imagination. It's always new stuff to learn, even if you're not doing, you know, cutting edge science. A lot of people going into these scientific technical hobbies thinking, you know, they're gonna win the Nobel Prize and like, well, it's not about that. I mean, yeah, maybe there's a tiny possibility that you might stumble over something that ultimately leads to something really cool. But mostly what you're doing is what we call repainting the masters, right? You're doing observations that literally thousands of other people have done before you, but that's no different than amateur optical astronomy. You know, that picture of M31, it's gorgeous, but 400 other people did it in the last month.
Unless you're Astronomy Live and you get to name a comet.
Well, okay, fair enough.
But
fair enough.
Like you said, that's that
you know,
one,
there are
right?
exceptions.
That's that one chance kind of mentality.
Exactly. But that doesn't actually make it any less interesting, any less of a personal technical challenge, any less of something that you can tell yourself, I accomplished this. So I don't mind that aspect at all. I remember when I built my very first serious radio telescope over 20 years ago. It was a 12-foot dish in our backyard when we lived on our farm. I remember the very first time that I did a transit scan in continuum of Cygnus A, which is one of the brightest sources in the sky, and it's 750 million light years away. It's almost a billion light years away. And I saw the trace slowly coming up and forming this really nice Gaussian. And then I called my wife in. I'm like, look at that. Look what I just did. And she's like, what? It's just squiggles. I'm like, no, you don't understand. The photons that are making those squiggles happen left the building 750 million years ago. Right? That's why it's exciting.
And to expand upon that, the sky is vast. And the amount of radio telescopes we have looking at the sky is small, for the sake of another word, minuscule almost. So you could, as an amateur, find something. You never know.
It's conceivable. Things like finding the afterglow of a recent supernova explosion that nobody knew anything about, although that is less and less likely with observatories like my brain has farted. The big new optical telescope with 3.2 gigapixels. Yeah, the Vera Rubin, thank you. Because they're scanning the sky every night. So they're likely to find these things. But being the first, for example, to discover the radio afterglow of a supernova remnant, that would be very cool. And it's definitely doable with an amateur instrument. So
definitely.
And as Dan alluded to, the sky speaks to us in like so many different wavelengths that most people are not even aware of. The radio, for example, has allowed us to explore the dynamics of the galaxy much more so than optical, because a lot of the stuff that you would like to see with optical is obscured. But radio has no problem.
And like to your point, you're talking about the Rubin Observatory. They have adaptive optics, which are like 2,000 little, motors that are, basically applying corrections so they can optically look through the atmosphere and make corrections. In radio, we don't have that problem per se. They have different problems.
Not generally, until you start going way up there, like in millimeter wave stuff, you don't generally have those problems.
It is very obtainable and is something that hopefully someone becomes interested in, to be perfectly honest.
Well, the really neat thing is that there has been this decades-long synergy between radio astronomy and commercial use of radio stuff. In particular, low noise amplifiers, there's been this constant back and forth in developing lower and lower noise FET amplifiers. And it's been contributions from both the radio astronomy community and the commercial telecom community, where commercial telecom goes, oh, we can build these things and that will allow us to do this thing. And then suddenly radio astronomy is, oh, commercial people are building these things now. We can build them for, $20 a piece.
And it's funny you bring that, because an episode we'll have coming up on the channel for Reality Checks goes into at length about Larry Basinger. And you helped me with that script. We were talking about, the engineering that kind of went involved for this gentleman who was an RF engineer. He worked at a radio station in Louisville, Kentucky. Naturally born skeptic, was trying to listen in on the Apollo 11 communications, because he wanted to know if there was going to be something that happened that NASA didn't actually broadcast. Now, we're not talking about aliens and things like that, but he just wanted to know maybe if there's something bad that happened and, it wasn't broadcast, it wasn't part of well-known knowledge or things like that. And he inadvertently ended up becoming one of the best independent witnesses ever for the Apollo 11 landing. Again, from an antenna that he built in his backyard with a low noise amplifier that he built himself, rebuilding the front end of a tank, a World War II or Korean era tank radio to be specifically built for the Apollo 11 mission that he had a year to do. And again, he became a legend within the RF community by pulling this off. And this is the same type of things that Marcus is doing and stuff like that. It's that same sort of mentality, if that makes sense.
Yeah, I mean, you and I did all of the analysis of whether this, given the early 1970s, late 1960s technology that was in play at the time, would this have even been possible? And the answer was, yeah, absolutely.
And again, so I turned to the expert that I knew to help me out with this script, because obviously I knew it was possible because I trusted an engineer to actually say this, but when you deal with a debunking or conspiracy crowd, you have to make sure you dot every I and cross every T. And Brandon Lee's principle becomes your life. So a 30-second video that was on TikTok spurned me doing a 2-week-long RF engineering sort of script with input from Marcus going over certain things, and then trying to scale it back into not just gibberish technical jargon to where people can actually understand it. So, and it's because the communicators like Marcus, people like Kate, people like Astronomy Live, people like Gabe from Saver Parts is they're doing the same thing, and they make it basically attainable for all of us. So you should be, I'm sure you already are, but if you're not, you should be subscribed to all those channels and looking through their videos to learn new things. Gabe is definitely a master of MacGyvering things and repurposing things, and Kate is right there as well, because she does things that I'm still trying to wrap my head around. So, and I say that with the utmost respect for all of you. And I appreciate you guys all being here.
Something that we might want to do, is we could set up a Discord channel for people who are serious about doing this. Where we could help them, point them at equipment and techniques and software and all of that stuff to help them along. In the ham radio community, we have what are called Elmers, and we could be the Elmers for people wanting to do
absolutely.
this.
We'll go ahead and throw it on the Unfornicated channel.
Too.
And if anyone is watching this video and not sure, if you go to the channel description, there's a link for the Discord is there. And if not, you can always shoot me an email and I'll get you a link. Well, with that being said, I think we can wrap up for tonight. We've been going for over 2 hours, almost 2.5 hours now. So I think it's time to go get some grub. I want to thank all of our panelists for being here. I appreciate it. You guys want to go ahead and wave goodbye to everybody real quick? And I'll go ahead and do my closing out, and we'll do a nice little transition. Bye, everybody. All right. So real quick, if you're here, I appreciate you guys being here and sitting through this. Hopefully you guys were able to learn something and glean something from this. If you didn't, that's fine too. At least you watched the video. If there's anyone who wants to put comments in the video, they're more than welcome to. We're happy to answer them when we can. And as always, thanks for staying here. So typical outro kind of goes in hand, and that is going to be, as always, stay uncensored, stay unapologetic, and by all means, stay unfornicated. And make sure that you always have your receipts. So we'll go ahead and play a song on the way out here, if I can find my damn music video thing. Here we go. And we will see you guys all on the next episode.
Scrolling feeds of endless dread.
Thanks.
Thank you.
It should be noted that while Marcus was going over that wonderful presentation, Mikey was doing a live stream.
Oh, really?
And it was yeah. Well, no, it was, I don't know what it was about because I couldn't listen and I didn't care. But it was apparently something about his lasers that he shoots in the sky that is so dangerous.
Oh my God. Oh yeah. He has a high power laser. Yeah.
Yes.
Yeah.
Yes. He has like burning blue lasers, 7 watts, I believe. He points them at the sky. He doesn't check for air traffic or anything.
Oh no.
Man, somebody, maybe me, should report him to Transport Canada because that is so incredibly illegal. You are required, if you're going to be doing like a laser light show, you're required to get clearance every single time from Transport Canada. and you have to receive training and be certified in the use of lasers that go up into the sky. Like, he's violating in so many different ways.
There was one live stream where he was showing off his 7-watt laser and he pointed it at his webcam.
Oh, nice. So there, afterwards, there was a nice splotch in the webcam.
Oh no! It completely borked the whole thing. They can't buy the webcam.
Excellent. Excellent. Yeah.